So I'm Konstantin Shvachko. I'm a long-time HDFS committer and right now chief architect at OneDisk, working on big data products, including non-stop HDFS and non-stop Hadoop. So we'll be talking about survival in distributed file system. So there's lots of distributed file system. Everything are distributed, like societies. The human body is a distributed system by itself. Cluster of computers is a distributed system. So how distributed system works? The parts of that system, individuals, they can work for a while independently of each other, but sometimes they need to do a common action in order to achieve a particular common goal. Then they start communicate with each other and make decisions and then execute on those decisions. So for computers, basically they're talking about numbers, so they're coming into an agreement about numbers, and they use algorithms to coordinate those agreements. So today we'll be talking about coordination engine, what it means. I'll then explain how we implemented it to build a non-stop HDFS with replicated namespace. Then we'll talk about HDFS that runs on geographically distributed data centers, and we'll talk a little bit about HBase because this topic was covered yesterday by my colleague Konstantin also. And I'll talk a little bit about potential benefits for probably all Hadoop, for the whole Hadoop ecosystem. So let's talk about coordination engine in general. Coordination engine is a very simple thing. So it produces a sequence of agreements, and based on those agreements, the distributed systems that participate in the system do some actions. So the main principle is that anybody can propose, and the coordination engine produces a single agreement every time, and then everybody who observes that agreement can act accordingly to that agreement. If they act deterministically, then the state of the entire system will be consistent with each other. So this is the simplest example I could come up with to demonstrate what a coordination engine is. So on the first step, there is a proposing step. So we have a set of proposals. Gumballs are proposals in this case. Then we trigger the coin mechanism, and that initiates the agreement process, the coordination process. And in the end, we choose a single agreement that comes out of that machine, and observers can learn that agreement and execute some action. So the action is not assumed to consume that gumball. The action is to keep it somewhere. It's a color code to do something, like, for example, orange could be go subscribe for OneDisk webinar, and green could be tweet send a Twitter update about Hadoop Summit. So let's do it again, because this is sort of, if we get to understanding of that I would consider my the goal of this presentation performed 75%. So this is proposals. We're proposing then coordination engine is triggered, and that produces an agreement, and we get a result, which is a color-coded action. So we've done it twice, so we produced a sequence of events, so all observers can take the same action based on that sequence. The simplest coordination engines that we've seen just now is a single node engine. It is a very important example of coordination engine. Name node, for example, was used as a single coordination engine all the time for many years. It's not reliable approach because that single node engine is a single point of failure. So what we actually want, we want something distributed. But it turns out the problem of coordination becomes really hard. And why is it hard? We can see on the two generals problem, a well-known problem. So basically, you should imagine yourself a general, and you design that genius plan how to attack your enemies, but you need to coordinate with your lieutenants when the battle starts. And different things can happen. So you basically probably sending, this is messenger, if you can see it. So you're sending messengers to your lieutenants, but your enemies are not sleeping. They are trying to kill them. And lots of failure scenarios can arise here. The messenger can fail at any time. And you don't know whether he actually failed or was just wounded, so it can recover and proceed. And that means that the message can be lost or delayed. The general itself is also not sitting, so he can send another messenger, and that messenger can duplicate the message or send a different message completely. And those messages can come in a different order, so your lieutenants will not know exactly or disagree on when the battle should start. So what's a distributed coordination engine? It's a set of nodes, and the nodes can play those three main roles: proposer, acceptor, and learner. Any node can combine any of those roles. So how it works, any node submits a proposal, but in this case, the coordination is going through multiple nodes. So they need to agree on something common between them. And after the common agreement is achieved, learners, which could be the same nodes, will update their state according to that agreement. So the difficult part here is the algorithm of agreement between those acceptors. So between those three acceptors, they need to sort of come into common ground and get that single agreement. When people talk about consensus algorithms, they usually refer to a two-phase commit, which is a simpler version of consensus algorithm, or a Paxos. Paxos was relatively recently developed by Laszlo Lampert. He was the first. And it has multiple implementations and multiple variations. At OneDisco, we have one implementation that is pretty general and has a lot of features and supports all common failure scenarios. Other examples, of course, Zookeeper, Raft. Let's talk about HDFS, the state of the art. I mean, you've probably been already on HDFS talks and very well know what HDFS is. So it's a distributed file system which has two main goals. First is to reliably store large sets of data, and second, to efficiently stream them to the client. Metadata, which is also known as a namespace, which is a hierarchical tree, which is a tree of directories and files, separated from the file data. Single name node stores all that information in memory, and data is split into rather large blocks and stored as local files on data nodes. So this is typical HDFS cluster. As of Hadoop 2, it has one name node, active name node. It has one standby name node. It has multiple clients that are talking only to the active name node. They send all their requests, and data nodes report to the name nodes. So this is the standard HDFS operation, I mean general HDFS operation. From the active name node perspective, the workflow looks as it receives a request from the client. Then it applies necessary update to its memory state. Then it writes a transaction log and then returns to the client. So from the client perspective, it's sending a request. Usually it's a read or write. By read, I mean requests like get block location or get file status or list a directory. By write request, I mean create a file, make a directory, or add a block. So as the result of that operation, it will receive from the name node a sequence of locations, and based on those locations, it will communicate with data nodes and stream either into data node or from data nodes some data. And data nodes transfer block between each other and from the client and to the client. And they also report their state to the name node through heartbeats or block reports. So we extended name node, and in order to distinguish it from the name node itself, we called it consensus node, or sometimes you'll see C node. Consensus, there are multiple consensus nodes on the cluster. Consensus node, all of them play equal role, so they're all active. You can send read and write requests to all of them, and this request will be consistently applied to the namespace. And the namespace is also the same on all consensus nodes. So when you update namespace on one consensus node, it is transparently, meaning that without client seeing it, it transparently propagated into other consensus node. And in order to make that consistent, we use coordination engine. So in this case, coordination engine serializes all the updates that come from the clients and apply the same deterministic updates in the same deterministic order into all consensus nodes, and that's what makes them what makes the state consistent. So this is a visualization of the cluster with data nodes omitted from the picture. So basically, you see that clients can talk to any of the consensus nodes, and in response to the client request, the consensus node can submit a proposal. The proposals are submitted only for write request, except some special cases, which we'll talk a little bit later. So that allows us to load balance both read and write traffic on the name nodes. We know that it's very easy to saturate name node with some stupid job. Happens all the time on big clusters. So proposals go to coordination engine. Coordination engine comes with agreement, for example, add block agreement. And then that coordination engine delivers the agreement to all consensus nodes. At that point, all of them execute the same add block, and they add a block to the file, and that delivers a consistent update of different replicas of the same namespace. So in general, as we've seen on the HDFS slide, from consensus node point of view, we added one single action to the, which is a coordination engine. So once the consensus node receives a client request, it submits a proposal instead of immediately applying it into its memory state. Then, when the agreement is achieved between those by the coordination engine, that agreement comes to all of the consensus node and executed. HDFS client and data node operations remain basically unchanged. I'll talk a little bit. There's minor change to HDFS client. This is a strict consistency model, not eventual consistency. It's called in traditional replicated databases one copy equivalence, which means that every replica of the namespace acts as a single copy. So again, the role of the coordination engine is to transform multiple requests that come from different clients into a consistent and global sequence of agreements. And every agreement gets a unique number, which is monotonically increasing. And by that number, the agreements are ordered and applied to the namespace. So if, for example, agreements to create a file in a directory that is not accessible for that user was sent by the client, when agreement comes, that operation will fail. But it will fail on all the consensus nodes consistently. And the client will get a reply from the node which originally received the request, will get a reply that permission denied or something. So also it's important to note that clock don't make any clocks, and time are not very meaningful in distributed systems. So so the consistency is by that global sequence number. So when consensus node when you take a snapshot of the consensus node state at particular GSM, then all those snapshots taken at the same GSM on different nodes will be the same. So that's the consistency we're talking about. So that's the only modification to the client that we did. There is in HDFS there is a configurable, pluggable class that's called failover proxy provider. Oops, proxy. proxy provider, so we replaced it with our own class, Cnode proxy provider. And what it does, it randomly chooses a consensus node, which it will send that request that the client wants to send, and send it there. Then it becomes sticky. So until that consensus node is fine and is responding good, it will continue sending those requests. But if request times out or something else happens, it will switch over to another consensus node. And we make it smart enough so that it avoids safe mode, because remember, any consensus node can fail. So if it fails, then at some point administrators will restart it, and there will be a period of safe mode when you don't want anybody to connect to it, because you'll get safe mode exception, which is unexpected in this case to the client, as they know the cluster is up and running and been running for a while. Of course, there are improvements that we can use here. One of them is choosing a consensus node that is closest to the client. Stale read problem can happen in two main cases. First case is when the client tries to, for example, create a directory on the consensus node 1, which is running at GSN 900, and then list that directory from that same node. It is sticky, so it will go for a last to the same consensus node, but that request times out, right? So it switches over to another consensus node, but that consensus node is running behind. And they can run behind for different reasons, because just the rate of the load on the consensus node can be uneven. So the second is more, and that problem we can solve by just making the proxy smart enough to wait until that second consensus node catches up and gets to 900. After that, it will be able to see make dir that it wanted to list, right? The second problem is a little harder because when the MapReduce starts, the client submits a job, and after submitting, other clients mappers will try to read that job file, and if they're not lucky, they can hit a node that didn't create that file. So in that case, we use coordinated reads. Coordinated reads means that the consensus node will submit a proposal to coordinate that read, and it will be actually executed only after the agreement comes to the consensus node. So it's a slowdown, but we optimize it by that. Once the file was read by some client, then we mark it that it was read, and after that we don't coordinate the reads. So block management, we divided block management functionality into two main functions. First is the new block generation, which is very important that any node should be able to generate a new block. And the second functionality is replication and deletion, and that functionality should be dedicated to a single node. Because bad things can happen if, for example, different consensus nodes decide to delete the same replica of the block, then you can lose all the blocks. Or if you replicate them twice, then you get an over-replicated block. So we call that node. It's the same consensus node. It's just an additional role on it, block replicator. And block replicator is elected using the same coordination engine. We made another step in replicating consensus node over the WAN. And in order to distinguish them from name nodes and consensus node, we call them Geonode because it's a geographically distributed file system. So our main requirements, of course, are that the system should still be the same HDFS. So it's a single cluster. It's not two clusters running on two different data centers. Parts of the clusters running on different data centers should have the same equal role. So you can do ingest of data on one data center, it appears on another. At the same time, you ingest another stream of data on another data center, and it appears on the other side as well. We want the clients to run with LAN speed. If you run, for example, a teragen, right, on one data center, you want it to complete as if there is only one data center. As if the cluster is only on that data center, and that's our requirement. And of course, we support multiple failure scenarios that any Geonode can fail. There could be multiple Geonode failures, and the whole data center can fail as well. And we want the cluster to be functional. Plus, of course, standard failures of data nodes, as Hadoop does these days. An HDFS cluster that spans across geographically distributed data centers looks like this. Data nodes in this case communicate data nodes. These data nodes on data center 2, for example, will communicate only to Geonodes from data center 2. So there is no communication across data centers. So they will send heartbeats and block reports only to their what we call native Geonode. So we distinguish between forms. Anything that is on another data center is called foreign to this, and native means that it's on the same data center. And this relative, of course, notion. So our design assumes that metadata is replicated instantaneously. Basically, when you submit a proposal, you update all the Geonodes on all data center as the result of the agreement. But the data is pipelined only on one data center. So if, for example, we are on, let me show you the picture. So if, for example, you are on data center, the client is on data center 1, it submits a request to the Geonode from that data center. Geonode replies with a set of locations. Those will be native locations that describe data nodes on that data center. Then the client will create a pipeline and start streaming data to this typically 3 data nodes. At this point, there is no cross data center. There is no WAN replication happening, and the client will continue working. That is creating another blocks or creating new files after it receives a confirmation from that pipeline. Client can continue working after that pipeline finishes. After that, some background events started happening. So first of all, these data nodes from data center 1 will send a block received confirmation to the data node, to the Geonode. So the Geonode, when the replication reaches the full replication, which is 3 in this case, will send first a foreign replica report. This is a proposal. So the Geonodes, consensus nodes don't communicate with each other at all. They just submit proposals. So it will submit what we call FRR proposal, foreign replica report proposal, and that proposal will inform another data center about replicas on these Geonodes. Also, it will schedule a transfer of one replica to a foreign data node, to one foreign data node. So we do not. We send across the WAN only one replica. This is for, of course, performance reasons. And when the data node receives that replica on data center 2, it will send a block receive to the Geonodes. And these Geonodes will recognize that this is an under-replicated replica, and it will trigger an internal native replication on data center 2. So when all the 3 replicas are created on data center 2, that Geonode will also send a foreign replica report as a proposal. And that way, data center 1 Geonodes will learn about foreign replicas belonging to data center 2. So that's the general scheme of replication. So foreign replica report itself is sent in 2 cases. First, when the count of replicas, of native replicas, reaches full replications, 3, or it drops to 0. Between those 2 values, each data center can replicate natively its replicas. When there is no replica, I mean, somebody needs to send that replica across the WAN so that that data center that lost all the replicas could start producing new replicas from a local copy. Foreign block management is a little bit different. First of all, we use designated block replicator per data center. So this is in order for those deletions and replication of native blocks could be managed locally for each data center. And also there is a new function on the block replicator which is monitoring foreign replication. So when it sees that there are no foreign replicas for some block, it will send schedule a replica transfer from the data center it's running on to another data center. So we implemented selective replication. These are requirements and 2 main ideas that we introduced some data center specific attributes. One of them is data specific replication of the block. You can say that replicate this block 3 times on data center 1 and 2 times on data center 2. And an interesting corner case is replication zero, which means that this data should not ever be replicated on that data centers, and our customers are saying that this is very important due to some regulations specific for different countries. And really quickly about HBase. So this is HBase architecture. It's a large sparse table that is dynamically partitioned into what's called regions, and that regions are loaded into memory and then served in real time to the clients. So regions belong right now. They belong. Every region can. A single region can be served by a single region server, and that causes a problem because if that region server dies, then several regions will be not available for the applications for some time. It recovers, it reassigns those regions, but there is a hiccup that we want to avoid. Sorry, these are edge-based operations. And the problem is, so natural idea is to put that, to replicate, to serve that region on multiple region servers, but how you do updates of that region, right? That should be coordinated. So we use coordination engine to do that, and coordination engine in this case works exactly as we talked before. That is, an update to the region is a proposal, and when agreement comes to all those region servers, they update the corresponding region in a consistent way. A few words about future benefits that we can derive from introducing a coordination engine in general into Hadoop ecosystem. For HBase itself, it can provide atomic updates of multiple rows. Right now, it's not guaranteed that atomicity is not guaranteed for if you want, for example, to delete one row and create the same row but with a different key. It also can, you can achieve, you can support secondary indexes. Secondary index is another table. And so if you want to, for example, if you are updating some row in the primary table which affects the secondary index, that could be done in a coordinated manner. And basically what you get by introducing coordinated updates, you get asset transactions, and that's a great advantage. So in the last minute, I wanted to thank everybody who stayed long, and also to thank the team that worked. It's a pretty big team that worked on those products. It's not a design, it's a description of working products. This is referred to Nonstop and Geonode, and HBase is a work in progress. We have a couple minutes for questions. Yes?
I have 3 questions. So which coordination engine are you using? Is it Paxos or some other coordination?
Right, that's what I said. We have at one disk, we are lucky to have a patented implementation of Paxos algorithm that's been in production. It was used in Subversion for several years.
How do you actually deal with failures of consensus nodes? Suppose a consensus node goes down for some time, comes back after suppose the statement, how does it sync up with other consensus?
Right, so if it comes back, for example, in 5 minutes, then it's not a big deal. The coordination engine itself will feed the agreements that it missed, and it will catch up on the agreements. If your failure was, for example, several hours, right, then that would be a very long list. So what we do is we make a checkpoint with the existing consensus node, which we call helper, right? And this is a standard HDFS checkpoint. It uploads the image, it rolls the edits, uploads the image and edits, then reads them, and after that, it replays the agreement that arrived after that checkpoint. The what?
The seek proxy
Uh-huh.
to make sure that the client won't consider the failure.
Yes, the consensus node proxy will make sure that the node that is not completely up, that's in that process of consuming, of catching up on the state, they will not let clients to connect to that node.
And also, what is the performance hit you observed because of this coordination process compared to existing in-shape solution?
What we observe? Performance issue. So, right. So I don't have figures on my slides, but what we observed, we did some benchmark with consensus node, which is LAN version, and we did with WAN version. So there is a latency degradation if you run, for example, NN throughput benchmark, right? Which does lots of small name node operations and doesn't. But if you run DFS-IO, then there is on LAN for consensus node, there is no degradation in throughput performance, and on WAN sometimes we see degradation because there is lots of transfers going on, right, over the WAN, that background transfers.
So, is there some mechanism to relax the consistency model? I mean, you're always talking about a strong consistency, but there may be some clients who are okay with eventual consistency. Is there a way to set the consistency?
So I don't know, should I repeat the question? Okay. So strong consistency, we claim strong consistency. If some clients can live with eventual consistency, what do we do, right? So we think that if we can support strong consistency, then the clients that would have lived with eventual consistency will not complain about strong consistency, right? So
probably can make some performance improvements for eventually consistent.
right, but eventual consistency also, requires some work, right? So here it's sort of isolated very nicely. I mean, there is coordination engine, which is a separate layer, and it just coordinates. That's it, right? And with eventual consistency, you need to put some hooks here, hooks there. I mean, do it in the right order, right? Yes, please. Sorry. Right. So there's several advantages that you can derive from here. For example, you don't need, by the way, that maybe also answers your question. If you don't need, very, very good reliability, you can, for example, run the consensus nodes without Edits law. Just write into dev null, right? And as long as you have at least one consensus node keeping its memory state, you're good because you can start other name nodes and they will get up to speed. And also answering your question that there are different interesting configurations that you can use. Some nodes don't need to be acceptors, for example. They can be only learners, right? And that's sort of your standby scenario. And we use that actually in the geographically distributed, in the WAN version. Because sometimes you want jobs run faster, then you put all the acceptors on one data center, and the other data center is just learning, right? And then, for example, if it's daytime in Europe, that works well. Yes, please.
Is there some sort of parallelism with your
last question? Sorry.
Consensus or your current And in case of having write locally, actually serve all operations via single script.
Right. So the question is basically comparison with Zookeeper. So our implementation of Paxos is not leader-based. So we don't have a single leader which everybody is talking, submitting those proposals, right, as in my gumball machine example. They can basically they propose locally. This coordination engine is just an abstraction, but it actually runs inside the name node in the same JVM. Okay, I have to cut it off. Let's take it offline. Sorry.